It's wonderful to see such a full theatre for this exciting event tonight. Hopefully everyone who's still coming in gets a seat. Wonderful. So welcome to the New England Aquarium and the IMAX Theatre, for this is the 6th annual John Carlson Lecture, and we're delighted to present this in partnership with the Lorenz Center of the Department of Earth, Atmosphere and Planetary Sciences at MIT. And for me personally, I am Nigella Hilgarth, and I'm the President and CEO of the New England Aquarium. This is one of the favorite events of the year for me. This is something I feel understanding climate is an incredibly important part of the education of everyone. And I feel that this lecture series is not only really entertaining and interesting, but really important in that sense too. We all know the climate is changing, we see it ourselves, and we hear a lot about what's happening to the ice sheets. I used to work on penguins, and I actually used to work on penguins that tend to live in warmer climates. But I have been to Antarctica 3 times, and over 15 years I've personally seen really quite dramatic changes in that area. And we're going to hear, I think tonight, I'm looking forward to hearing about big ice by one of the world's experts and one of the world's best speakers on the subject, so I'm very excited about that. Just want to say before I hand this over that the Lorenz Center at MIT brings the best scientific minds together to study climate and how it works. And at the aquarium, we really share the Lorenz Center's desire to explore and to share raising the level of public understanding and attention to these issues of global change. I believe that information becomes more meaningful as we discuss it and we consider how to use it to shape our behavior. And armed with data and knowledge, we can make changes where needed to correct our course and to persuade others, including policymakers. And so it's my great pleasure to thank John Carlson and the Lorenz Center for making the New England Aquarium the home of the John Carlson Lecture, and we're looking forward very much to Richard Alley's talk tonight. So now please join me in welcoming Kerry Emanuel and Daniel Rothman, who are MIT faculty members and the co-founders of the Lorenz Center at MIT, who are going to introduce our speaker tonight. Thank you.
Well, thank you very much, Nigella, and particularly thanks to your wonderful New England Aquarium staff who've been so helpful in setting up these lectures. I also want to extend a special welcome to our sponsor, John Carlson, without whom these Carlson lectures wouldn't take place, and to extend special thanks to his friends and colleagues who are here tonight as well. As Nigella said, I'm Kerry Emanuel, and together with my colleague Dan Rothman, run the Lorenz Center, which is devoted to curiosity-driven science, climate science in particular. This is the 6th annual public outreach lecture of the series. Let me ask you before we begin to please hold your questions during Richard's talk, and we'll take questions rather systematically after the talk. It's a great pleasure this evening to introduce my friend and colleague, Richard Alley. Richard is the world's foremost expert on the relationship between ice and climate, what ice has to tell us about past climates, the role that ice has played in climate change, and the relationship between continental ice and sea level. He is also the most energetic and entertaining public lecturer I personally know, living proof that fire and ice somehow go together. We are very fortunate to have him here tonight. Richard is the Evan Pugh University Professor of Geosciences at the Pennsylvania State University. He's been there more or less continuously since he got his doctorate from the University of Wisconsin in 1987, in spite of many enticing offers from institutions closer to sea level, preferring the high terrain of Pennsylvania for reasons you will hear about presently. He's a member of the U.S. National Academy of Sciences and a foreign member of the Royal Society of England. His list of awards is so voluminous that it would take the better part of the evening to recite them, but I do want to mention that he received the highest university-wide teaching award at Penn State for reasons that you are about to discover. Richard has done more than just about anyone I know to bring the excitement of climate science to the public. In 2011, he published Earth, the Operator's Manual, which was turned into a 3-hour TV series on PBS. My personal favorite is The 2-Mile Time Machine, Ice Core's Abrupt Climate Change in Our Future, which won the Phi Beta Kappa Science Book Award, among other awards. He has published several other books as well as over 250 refereed papers. But I wish he'd slow down on reviewing papers. I once complained to a journal editor that I was being asked to review too many papers, and the editor shot back that Richard Alley reviews 2 papers per week, forcing me into meek submission. The Carlson Lecture is meant to convey the excitement of climate science to a broad audience. It's hard to think of a better person to do this than Richard Alley. Please welcome him.
Oh, dear. I'm not sure what to do after that, but thank you, Carrie. Thank you, Dan. Thank you to John. This is a fantastic event, and I have looked at the previous speaker's presentation. It's just fantastic, and thanks to Nigella. It is what you have here, right? So I spent the afternoon with my dear wife Cindy over at the aquarium. We got there in time for penguin feeding, so you know, when we love penguins too, and this is just a world-class facility. And the opportunity to have this is you know, we're flattered and honored to be a part of it. So thank you. In case I don't live up to Carrie's introduction and you need a nap, what I'm going to do is walk you through what big ice sheets do, how they record climate history, what they mean for sea level, just a word or two about how they make beautiful landscapes, and a little bit more. And then we'll finish it up and take a few questions. So that's where we're going to go. I want to start with a little climate history for you. So you're looking at a picture a little bit west of here. So you can tell where you are. There's Lake Michigan. You can see Indiana and Michigan and Illinois. And this is a digital elevation model, which was very carefully shaded by my friend Tom Lowell to bring out the footprints of an ice sheet. And the ice sheet that did that was there. It came down from Lake Erie. It came down from Lake Michigan. It was bringing the soil and the mud of Canada and depositing them down here. And then, you know, eventually it sort of wobbled back as the world warmed. And eventually it went away, and you look at it and you say, wow, the climate changed. And anyone who's ever seen a footprint, there it is. The world changed, and that's right there. You will occasionally hear someone say, oh, if it gets warm, we'll just go up to Canada and we'll grow our corn. No, you won't. Because the soil that you grow it in is down in Illinois growing the corn. Now, if that's a little too far west for you, I'll give you the same picture, a little closer to home, so there you are. And, you know, the Cape Cod lobe came right down the middle there, and there was another one out towards Georges Bank, and you live in the footprint of a great ice sheet. And it was a fascinating footprint. We like to go out to the Cape when we get the chance, and it's there and it's beautiful because the ice did it. Here's a picture showing on your left over here where the ice was 18,000 years ago. It had just started melting back. 24,000 years ago it was its biggest. 18,000, it's just sneaking back. And you can see it across chunks of Europe, across North America. And then over on your right, there's the little weeny bit left on Greenland. That's still 23 feet of sea level, so the big one was big. I can fill in the south. The south is not nearly as dramatic. You'll see a little bit of Ice Age ice down in Patagonia, and Antarctica got a little bigger. But the south doesn't have a whole lot of land at the right latitude to grow a big ice sheet on. So the action here is Boston up to Canada, more or less. And so let's talk about ice sheets. I'm going to show you how we read the history of an ice sheet. I'll show you why the ice came and why the ice went, and then we'll wander on for there. So here we're looking at the very edge of the Greenland ice sheet, and I can tell you, I've spent a lot of time looking at ice, and I don't regret it. It is a fascinating undertaking. And so what's an ice sheet? If it snows, usually it melts. Right? You try to make really snowy year, what do? They make a giant pile here, but it melts. But if it snows more than it melts, it piles up. And if it piles up and it piles up, eventually you get an ice sheet. And that's all it is more snow than melting in a big area for a long time. So I'm going to take you to Greenland first. We'll come back later to Antarctica, but I'm going to take you to Greenland first, and we'll visit a big ice sheet. So you get to the edge, right, and there's tundra, and the tundra is pretty. Here's a herd of musk oxen thundering through the forest in Greenland. That is a forest in Greenland. So, right, there's a little bit of willow and birch down there under the musk ox. Right, and these are caribou, reindeer, and if you go to Greenland at the wrong time and you go down in the tundra, the mosquitoes, it's hard to see through the cloud. And so the caribou run down on the tundra and they eat lunch, and then they go up on the ice because the mosquitoes, and so these are caribou avoiding mosquitoes. All right, okay. And these days, I come visit you and thank you, and I answer email and I teach classes, but I used to get on these big planes and I used to go up in the middle of Greenland, and so this is midnight on the 4th of July. We are 200 miles from the nearest rock. We are 2 miles vertically from the nearest rock, and we're up there doing ice coring, okay? Okay, so at the time I took this picture, you will notice here on your left that there are some newspapers. We had been there a month without resupply, 2 more weeks until the planes came back, so the newspaper is a month old. But if you look on the other side of the picture, you will notice that it really doesn't matter that the newspaper is a month old. It's perfectly fine. Now this one you'll notice is labeled a good day in Greenland because this is a bad day in Greenland. The wind blows, the snow blows, yeah, okay. Right, and this is 4th of July, so we went up there to work, and we worked, but 4th of July, you gotta kick back, so you can see the volleyball game. It's just about midnight, that's the midnight sun, and you can see Eric Saltzman, who actually hit into the snow trap, and you know, a month in, the laundry gets a little life of its own, so there's some freeze-dried laundry. So at any rate, so what we're doing here, in the red flannel shirt is Joan Fitzpatrick from the United States Geological Survey, and the guy without the shirt is me, okay? And you'll notice we have dug 2 holes, and there's a narrow wall between those 2 holes. And Joan's cutting a stairway, and we're gonna put boards over the hole that Joan and I are in and crawl down it, and you can see our stairway down. The sun is going to shine into the open pit, and it's going to shine through that wall, and we're going to see the layers of snow. Okay? And there they are. So this is a wall. I dug it as deep as I could throw the snow out of, and Joan's my size, so we don't go any deeper than that. And what you're looking at are the storms. And in summer, the sun comes up. It doesn't melt. It's too cold up there to melt. But it changes the snow because the sun is really intense. And so you can see sort of that lighter layer, and next to it I labeled summer. And then there's another winter and another summer and another winter and another. Snow is blue for the same reasons water is blue. And snow is layered because we have storms. And snow has annual layers because we have seasons. Now I can tell you that story, they're annual. We worked really hard on that. We worked on the physics of what's going on. We watched it. We watched things get buried. And we did a whole bunch of testing. You may know that in 1954, the US used a very large, very dirty bomb to blow up Bikini Atoll. Radioactive fallout goes around the world. It falls on the ice sheet. You can still find it. If you put a Geiger counter on a string down a hole in Greenland, you'll find 1955 where it fell. And we can count down to that. And we can say, do we get the right number of years? We know what year that is. Do we get it right? 1783. Ben Franklin is representing the young country in Paris. A dry fog comes blowing into Paris. And Franklin says, there must be a volcano erupting in Iceland. The people in Iceland knew. They were having terrible trouble because this volcano was poisoning their sheep. And Locke has a particular composition of ash, and we can find that ash in Greenland snow. We know what year 1783 is. And if we can count down to it and say, do we get it right? And for Vesuvius and all the way down, as long as we have written history, we can find markers and we can check, do we get it right? And I count, and Tony Gao counts, and Deb Meese counts, and we use chemistry, and we use a whole bunch of things. And when I tell you it's an annual layer, it really is an annual layer, and we have a lot of confidence in this. Okay? So now let's get an ice core. So we're going to drill an ice core, and here we are drilling ice cores. Catherine from Alaska probably has on her t-shirt, says big boots, big science. She certainly has on her big boots. And this is big science, because we're going to drill through 2 miles of ice, and we're going to take it. Here's Bill from New Hampshire slicing a piece of ice down in our secret under snow laboratory. And here's ice, right? These are ice cores. 1547 on the end of one of them there is 1,547 meters. It's almost a mile down, and it's 8,400 years, more or less. And so here we go, right? Wanda Kapsner there is cutting a thin section. Kurt Cuffey is looking at the ice core. And what Kurt is looking at is this. It's lying on its side now. Those light layers that you saw in the snow pit have trapped big bubbles, and they scatter the light, and they look dark here. And underneath it, you'll see winter, summer, winter, summer, winter. The layers are thinner because they've been squeezed and because the ice is flowing, but they're still there. Okay? And so what do? We have a team, not me, it's a whole bunch of us, and we get the age. And if I can tell you this is a year, and I know a little bit about squeezing snow to ice and a little bit about ice flow, that tells you how much it snowed that year. And in that, there is dust, and we can fingerprint the dust. A lot of it came from Asia. In that is sea salt, a little bit of pollen, forest fire smoke, micrometeorites falling down from space, odd isotopes that are made by cosmic rays breaking things in the air. Anything that's blowing through the air falls on the ice sheet. And if I know how much snow fell, and I know how dirty that snow is, I know how much stuff is falling, how many micrometeorites, how much dust, how much sea salt. In that, there are indications of temperature in Greenland. And in Antarctica, we'll get indications of temperature in Antarctica. I'm not going to spend a lot of time on them. They take a little more story than we've got time for, but I'll tell you one of them because it's just so cool and because Kurt Cuffey and I did a lot of work on this. You know, if you were stupid enough to touch a hot stove burner, you'd burn yourself almost immediately. But if you put on an oven mitt, you could pick up something hot and carry it to the table before you burned yourself, because that little thickness of oven mitt will protect yourself for a minute. If you try to cook a turkey, it takes hours to get hot in the middle. If you try to heat a 2-mile thick ice sheet from the Ice Age, it hasn't quite warmed up all the way yet. And if you drill a hole through Greenland, you wait a couple years for the heat from your drill to dissipate, and you put a thermometer on a cable. A mile down is colder than the top, and it's colder than the bottom because it hasn't warmed up from the Ice Age yet. And how cold it is tells us how cold the Ice Age was. And if that isn't cool, I'm sorry, that's just cool. Okay. It's way cool. Okay, so, and in there are bubbles, and the bubbles have samples of old air, so we can tell what the composition of the atmosphere was, and they're all together. So we can tell what was the temperature in Greenland, what was the snowfall in Greenland, what was blowing through the air, what was the air, all together. And as Gary said, I wrote a book on this, and I've helped write a bunch of papers on this. By itself, that isn't enough yet. We have to go talk to real climate scientists and modelers and a whole bunch of other people to make sense of this. But when we do, we start to make a lot of sense. And what we learn, a number of things, and you can see them behind me. We actually do have, a little indirectly, but we do have indications of how bright the sun was because it protects us from the cosmic rays that make beryllium-10 that falls on the ice. When the sun gets brighter, the world warms. When the sun gets dimmer, the world cools. But the sun doesn't change much. The sun is a very faithful and wonderful star that just sits up there and does its thing. And there's little tiny wiggles, but it's not a big deal. If the sun changed a lot, the climate would change a lot. But it doesn't. Okay? When a big volcano blocks the sun, it gets cold. If we had a big eruption tomorrow, next year would be cold, even with a lot of CO2 in the air. But big volcanoes aren't very organized. A volcano in Alaska cannot call up a volcano in Indonesia and say, let's go on 3. And so they just make noise. They wobble around. And so when you look at a change in climate, it's got some noisemakers in it of big volcanoes occasionally blocking the sun. You get the wrong website, you'll start seeing people get into weirdness. There's very little weirdness. There is not enough space dust to matter, and it doesn't change much. The last time that something from space really mattered was a meteorite that killed the dinosaurs 66 million years ago. We didn't have ice then, it was too hot. But space dust doesn't do it. There actually is an interval when the magnetic field essentially zeroed out. Lots of cosmic rays came into the Earth system because we weren't protected by the magnetic field. The climate ignored it. It's not a big deal. We can't find anything else weird or space-wise that's making the climate change. And we've looked. Okay? There are some features of ocean circulation, short ones like El Nino, and then longer ones that really do matter. We could talk about them at some point. I'm going to walk you through Earth's orbit. They're slow, but they're big. And then we'll get to greenhouse gases. And the more we learn about the history of climate, the more important greenhouse gases look. And that's an important piece of the story. So let me show you this. This is a temperature record I did not help make. This one's from Antarctica. And you'll notice the way we have it labeled. We drill from the surface down. So we often start with today over here on your left and old over. It doesn't matter much, but you can see. So this is today going down in time. This is temperature in Antarctica for 440,000 years. If you go elsewhere and collect a record, it will look a little different. But if you blur your eyes, basically every temperature record on the planet looks a lot like that one. Almost everywhere had these cycles, and that low spot right there, I'm circling for you, that's when the ice was most recently rumbling across Boston in that picture I showed you of Cape Cod. So you have ice on Boston right there, and you live up here. Okay? And if you look at that thing for a little bit, what you'll notice is it doesn't look like a random number generator made it. In fact, it doesn't look anything like a random number generator made it. It looks like a clock made it. And you can just sort of walk across the top there, and I can do it with my little pointer down here, but you can see it sort of going tick, 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 tick. That looks like there's a clock running. And if you were to look carefully, you'll see down in here there are preferred spacings in the shorter lived peaks too. There's an ice age cycle, and it goes warm, cold, warm, cold, warm, cold, warm, cold. And running on the back of that is going warm, cold, warm, cold, warm, cold, right? This is not a random curve. And it's a curve that was predicted by physicists, astronomers, 50 years before it was observed. And this is one of these great stories of science. Several people were working on this. The last one to pull it together was Milankovitch. And early in the 20th century, he said, look, there are features of Earth's orbit. And those features of Earth's orbit move the sunshine around on the planet. And when you climate historians finally get your act together, and you figure out how to make a history that's believable, you will find those features of Earth's orbit in your records. And it took 50 years to do it, and we did. People who taught me did, right? Yeah. So I want you to, for a minute, each of you now is the sun, right? So in your mind, I am the sun. I am bright. I am brilliant, okay? I'm the Earth, and I'm looking at you as the Earth, and as I look at you, if my North Pole stuck straight up, you could never give me a sunburn on my Arctic bald spot. But of course it's not. It's tipped over 23 degrees from the orbital plane. And that means that when I'm on this side of you, you can give me a sunburn on my Arctic bald spot. And then when my orbit takes me out the doors at the back of the auditorium, you're sunburning my South Pole, and we won't go there. But as I orbit you, I get sunburn on my South Pole and then my North Pole because I'm tipped 23 degrees. And as it's shown up there, this tip goes to 24 degrees and then about 22 degrees. That takes 41,000 years. A little more, a little less. When it tips more sun at the pole, less at the equator. More at the equator, less at the pole. More at the pole, less at the equator. More at the equator, less. Total amount of sun doesn't change. You're still shining on me. I'm still here. But you're moving it around. And there's also a wobble, and then the shape of the orbit changes. And this happen because there's a bulge at the equator because it spins and the moon and the sun tug on it. And then the orbit changes shape because every time we lap Jupiter, it tugs on us a little bit. And so these things happen, and they move sunshine around on the planet. And what happens when the summer sun goes down in Canada and Boston, ice grows in Canada. And when ice grows in Canada, the entire world gets colder, including the places that are getting more sun. And that's weird. Milankovitch said, of course you'll find my wiggles, but you'll find the ice age is running around because they have to run away from the sun. But what we find, the sun is going from the poles to the equator to the poles and from north to south. But the whole world gets warmer and colder together. Milankovitch never thought of this. And then you say, why? When Canada gets a little bit of sun and the ice grows there, why would the places getting more sun get colder? And the ice cores answered it. And it's the second plot. And what you'll see there is the concentration of carbon dioxide in the atmosphere. And it's not identically the same curve. There's a little offset and a little delay at certain places. But what happens when ice grows in Canada, sea level falls 100 meters, ocean currents change, dust changes, winds change, a whole bunch of things change. And several of those move a little bit of CO2 out of the air and into the deep ocean. And when ice melts in Canada, a whole bunch of things change back, and several of those move a little CO2 out of the deep ocean into the air. If you ignore the CO2, no one has ever explained why half of the world ignores its sun and listens to Canada's ice. If you include the CO2, it all makes sense. And so this is a fascinating story that started off absolutely unequivocally, this is not a CO2 story. But when we get done with it, we say, wow, greenhouse gases really do matter. And we can't make sense of climate history without them. Okay? Now, the fact that those two curves look like each other doesn't tell you anything beyond, wow, we should understand this. Something's happening. Something could be driving both of them. One could be driving the other. In this case, it takes a whole lot more to work with the dynamics people, to work with the chemists, to work through all the pieces of what's going on, to realize that the sun is kicking temperature in Canada, which is kicking some other things, which gets to CO2, which then gets back to temperature. But it actually does work. And it really does show us that greenhouse gases are important in this story. Okay. Now, I'm going to change gears here a little. I showed you Kurt Cuffey there a minute ago. Kurt, along with Stan Batterson, wrote a book called The Physics of Glaciers. If you ever want to study glaciers seriously, this is the book to start with. And so I'm going to go over physics of glaciers for you. Right? So this is the physics of glaciers, the starting version. If you make a pile, like a pancake, here we are making a pancake. My dear wife, Cindy, here is pouring the pancake for us. What happens when you make it? It spreads under its own weight. Okay? If Cindy puts her spatula in the way, what happens? That stops the spreading where the spatula is in the way. If you cook it, it gets stronger and then it doesn't spread as fast. If Cindy pours it on a waffle iron rather than on the frying pan with a little bit of grease, it doesn't spread as fast because the bumps are in the way. Okay? And you know I'm going to make an analogy to an ice sheet, so I want you to just think about which one of those is the Cape Cod lobe. So, okay, so what is an ice sheet? Snow piles, and it piles, and it piles, and it's a continent wide, and it's 2 miles thick. And it's almost warm enough to melt, and it spreads slowly under its own weight. And it is that pancake at a vastly bigger scale, spreading under its own weight. And snow on top adds to it, and melting at the edges or breaking off to make icebergs subtracts from it. And it tends to come to a balance where the snow on top equals the spreading equals the melting and breaking off. If you turn up snowfall, the pile gets bigger and the ocean gets smaller. If you turn up spreading or melting, the pile gets smaller and the ocean gets bigger. And then you worry about your coast. Okay? So I'm going to walk you through a little bit about lubrication at the bottom and a little bit about spatulas or flying buttresses. They're the same thing. So here's a picture of Greenland, a diagram, right? There's air over ice over rock. And as the ice flows over rock, occasionally it gets hollows in the surface where lakes form in the melting zone. We drill cores up in the middle where it doesn't melt, but down at the edge it sometimes does. But Greenland's sort of a waffle iron. You know, it's bumpy underneath. That's why there's the lakes. And so you get lakes. There's a lake on the surface of Greenland there. And here's a lake on the surface of Greenland with a stream flowing into it. And here's an interesting thing. Right? I'm going to do this with ice in a minute, but I want you to think first about a giant melted pot of rock under Hawaii. And that giant melted pot of rock under Hawaii wants to get out because it's buoyant, it rises. But a giant melted pot of rock never has a drill. Nobody sits in the earth under there with their Black & Decker drill and says, wow, I'm going to drill a hole. What does it do? It breaks a crack. And then it starts the eruption in Hawaii with a giant fire fountain, one of these 1/4-mile long things that's spouting like crazy. And then only later the thin parts freeze closed and the thick parts keep flowing in something like a volcano or a lava tube. Nature doesn't have drills. It breaks through cracks. So now go back to Greenland. This is a lake on Greenland. It is a few miles across. It is 30 feet deep in the middle. It is sitting on top of cracks because there are crevasses up there. It is trying to wedge those open. Down the road here a bit, Sarah Doss works at Woods Hole. She's part of, wonderful, wonderful work. Sarah and Ian Jockin were up studying this lake. Thank goodness they were not in the lake when it broke the crack. Right? Sarah is standing in the middle of the lake. You will notice that her feet are dry. Okay, where is the lake? It did that fire fountain upside down and it went to the bottom of the ice sheet. When it was doing it, it was twice Niagara Falls for an hour. The ice lurched up and it went sideways and there were earthquakes, and you see these big blocks sitting there behind Sarah. They were breaking out of the ice and popping up to the surface in the flood that was going on. It was truly fantastic. And that lubricated the ice, so it started going faster, but it didn't fall in the ocean. And why didn't it fall in the ocean? Because Greenland's sitting on a waffle iron. Right? There's bumps under there, and you can't fall off in a waffle iron into the ocean. So it mattered to lubrication, but it didn't go away altogether. But we modeled it. This is one that we actually, before Sarah observed this, we wrote a paper that said, when this happens, it's going to be something. And we did that by stealing all the volcanic literature and turning it upside down, because magma rises and water sinks, and otherwise it's the same physics. So it's just fascinating. Right, okay, so now remember Cindy and the spatula, right? And I'm going to draw an analogy and then go back to the ice. Piles spread. This building is so strong, it's like a cooked pancake. The walls are not bulging out, the roof is not caving in, and you're fine. The early Gothic cathedral builders got themselves in trouble. They built such vaulted, beautiful ceilings to heaven that the walls tended to bulge out and the ceiling tended to fall in. What did they do? They developed spatulas. They developed the flying buttress to help push back and avoid that spreading tendency. And without that, you lose the Gothic cathedral. Okay? An ice sheet has a spatula. It has a flying buttress too. So the pile spreads down to the ocean, and in cold places, it doesn't immediately make an iceberg. It remains attached, but it flows over the ocean. And it's almost always in a bay, a fjord, and that means there's friction on the sides of it. And that friction holds back the floating part, and that holds back the non-floating part. And the pile is bigger because this flying buttress, this spatula, is holding it back down there at the sea. Now, up in the middle, Antarctica is minus 50. You make it minus 45, it won't melt. But down at the coast, at the bottom, it's in the water. It's at the melting point. And at the top, it's really low and warm. It's almost at the melting point. If you were a bad person and you knocked out the flying buttress on a Gothic cathedral, you could harm the Gothic cathedral. And what we're worried about is what would happen if Sarah Doss's lake breaks out the equivalent on the ice sheet. And I'm going to show you what happens because we've seen it happen. So we're now down at the tip of the Antarctic Peninsula. So if you look in the little map in the lower right here, the tip of the arrow, we're looking at the Larsen B ice shelf. The ice shelf formed 10,000 years ago as the ice shrank back from the Ice Age. It has sat there for 10,000 years. On the left, you see it. That's the Antarctic Peninsula way up in the upper left corner. Black is the ocean. There's a scale bar over here. That's 12 miles or 20 kilometers. So those little white things in the ocean are bigger than aircraft carriers. And in between there is the Larsen B ice shelf. And on top of the Larsen B ice shelf are lakes. And they're sitting in cracks, and they're trying to break through the way Sarah's lake did. But under them is ocean. And so I will make that label go away, and then I'll make the ice shelf go away. And you can see what happened. This is 5 weeks. Okay? And the blue slushy that you see there is, when these fall over, it's really dramatic, and it breaks things up into little bits. You could kayak through that. It's broken up crud. Now, that did not raise sea level because it was already floating. But with it out of the way, the ice behind it sped up between 6 and 8-fold, and that does raise sea level. And, so floating ice doesn't raise sea level, but when you get it out of the way, it lets non-floating ice go faster, and that does. And what we're worried about, there's only a little tiny bit of ice behind that. You're not going to notice that one in Boston Harbor. But what we're worried about is that there's a lot more of these flying butts or spatulas down there. And if we make it too warm and take them out, you might notice it in Boston Harbor. Just a brief word here. You'll remember that we said the volcano starts as a fire fountain and then it goes to a pipe. The ice does too, so Sarah's Lake went through a crack, but later you'll fly over and there's a hole that the water is going down like that. And the water goes down these great holes, and then it goes shoosting out the front. This one's really cool. This is a glacier flowing into a fjord, and the fjord is choked with broken up ice, and you see that little circle in front of it? That's where the stream comes out from under the glacier and bubbles up through the seawater to the surface. And it's a little bit muddy because it's washing dirt out from under the glacier. Now you'll see that, here we're up on land where one comes out, and you see that one's really muddy. And I was with these guys who were kayakers. They spent the longest time looking at this river. And finally the one looks at the other and he says, "Nah, you're dead." But that's the stuff of Greenland being washed away down that river. And these big floods help wash it away. You see this is New Zealand, and you see the same thing there. If you were to wade across that river when it's flowing high, you'd get your ankle crushed because it would roll a boulder over it. And that contributes to making these glorious landscapes. And glaciers make not just Cape Cod, not just those beautiful moraines, but, Yosemite. There's Yosemite as it is now, and there's where it will be in Greenland someday. So you can see the similarity. It's just wonderful what they do. Okay? So you may possibly have guessed that I love ice. This is cool. You may also have guessed that I'm a professor. Okay. We have two wonderful daughters, and the kids used to say that I had a professor button. And they'd say, "Uh-oh, you push this professor button, get out of the way, he's about to profess." Janet teaches middle school science, and Karen is a grad school student working on glaciers. So whatever happened, we're very, very happy and very proud. But at any rate, as a professor, you know how this works, is that after you talk a little bit, you have to get to the point of reviewing. Then you're supposed to do a quiz. We won't do a quiz, but you're supposed to review. So I have taken the liberty of preparing a review for you, and it will take us about 30 seconds or a minute to get the review set up here. So I'm going to review for you Kurt Coffey's Physics of Glaciers, and we're going to review it in G major. So I'm passing the clicker to my dear wife, and thanks to Tommy for bringing his guitar down, and we have to get the microphone set up here just for a moment, and then we should be able to make this work, I hope. So we will see what we can do. And as I said, this is the Physics of Glaciers, honest to goodness. And we'll see if we can make it go. Nobody has ever accused me of being on tune, so don't worry about that. And you know this song. So are we on here? Good. Okay. So at any rate, we good enough, Cindy? Ooh, a snowflake out on a chilly night, over the ocean of blue and white. Southern Cross is a guiding light headed for South Pole. Oh no, Southern Cross is a guiding light headed for South Pole. Soaring through, the penguins flying, the krill fleck blue, got seals and skuas, great whales too, all playing right, there will not be a quiz, but for what it's worth, we do know a whole lot about the ice now. It is fantastic how much we've learned. My lifetime, we have gone from an amazing amount of ignorance to an amazing amount of knowledge. There is an incredible amount to learn. And if you have students at home, or if you're a student here and you want something fascinating to work on, come find us, because there is an incredible amount to learn. And I truly do believe that it's useful, it's valuable, and it will help us in ways that we can use. And so let's go find out. Thank you.
So that was fantastic. I don't need to tell you. So we have a fair bit of time for some questions. And so before I take your question, I want to ask any of the students in the audience, particularly the younger ones, the middle school students, to start the question period. We're going to wait. Surely. There you go.
All right, thank you. Cool, what's up?
What species of animal has been the most affected from climate change?
So what species of animal has been the most affected because of climate change? And I'm not sure I know the answer to that. So you can pick a lot of the really easy, glib ones. So polar bears are going to get hit because they rely so much on sea ice. Pikas are going to get hit because they're really cold adapted. Probably now the biggest worries, maybe things we don't even know about. So you think about what we're doing. We have a lot of us. And we have a lot of places that there's 1,000 miles of cornfield. And somewhere in that, there's a little bog, and in that bog, there's somebody who's hanging on. And they may not be very important, and they may not be very common, but that's what they do. And now the climate changed, and they need to get 1,000 miles somewhere else. And how do they get there? And so probably the initial real issues are how it combines with the other things that we're doing. The climate change we've done so far is still pretty small compared to natural variability, but we're pushing the system in multiple ways. And so the sort of the opportunities to be smart and to say, where are those things that are hanging on, and how do we design a world so there's a pathway for them to move forward? There's a huge amount of room for preserving biodiversity by being smart on these things.
Surely that was not the only middle school student in the audience who wants to ask a question.
Thank you, by the way. Yes.
Thank you.
Yes.
They're the student, right? Okay.
Right, so how did I decide to study ice, and what was the primary motivator? I desperately wanted to study geology, natural science. I wanted to be out. I love the earth. I was into this. I used to crawl around in caves in high school and collect rocks. And I went to Ohio State before Wisconsin, and I went down and took the first year classes, and I went looking for the professors, and I said, I want a summer job, what do you have? And I annoyed the professors, and one professor had a job cleaning fossils with a dental pick, and one professor had a job finding the fallout from volcanoes in the ice sheet in radar records, and finding the fallout from atomic bombs in the ice sheet from chemistry, and I said, I'm going to do that. And I'm still doing it. So it was a bit of an accident that I got into ice as opposed to air or ocean or rocks, but it was really intentional that I got into something like that.
Yes.
If the ocean rises like 6 meters, how would it affect Massachusetts?
Right, so if the ocean rises that much, how will it affect Massachusetts? Huge question is how Massachusetts deals with it. So the Orleans Rotary, Cindy's family has summered on Cape Cod for a long time. We go to Eastham, and you know it's about there. And you have to go across the Orleans Rotary, and the Orleans Rotary is at 12 feet, I believe, so 3.5 meters. So 6 meters, the Orleans Rotary is well underwater. So that's an issue. But the question then becomes, we rely in the ocean so much on wetlands for buffers, for biodiversity, for fish hatcheries, for seabird migration places. Do we allow those to move inland, or do we build a wall and smash them against the wall when the ocean rises? And so the question of what we do becomes really important. Are we going to build walls? If we build the walls, do we put a wave generator in the wall to get some power out of it or not? And so the sort of, do we respond to this in wise ways that take account of what we value and where we want to go, or do we not pay attention and then respond in ways that don't protect us and don't protect the natural world? And so it could be very, very, very expensive. We could build big walls. We could build valuable things behind the walls because the walls are supposed to make them safe. The walls could fail, as we've seen, and then you spent the money for the valuable things and the walls, and it all got wiped out, and it's a disaster. Or we could build resilience and adaptability into our plans going forward and minimize the costs. And so there's real opportunities here to be smart on the way forward.
Right there. Back, yeah.
If there is a cycle for the CO2 and global temperature, then what impact are we having on it? Because we are emitting more CO2 than interfering with the cycle.
Right, so if there's cycles, what are we doing? We have blown the cycle out of the water. So the cycle was doing 180 to 280 parts per million by volume over about 10,000 years. And we have done more change than that in 100 years. So we are changing it so much faster that essentially the natural cycle, recently the natural cycles have been fighting us just a little bit, but we're just beating them all hollow. So this is one, and it maybe, and thank you. It's worth a comment, I think. The climate has always changed. The climate would always change without us. And those of us who are climate historians, by studying these past changes, are becoming much clearer in how important the human influence is. If you were CSI whatever, and you were an arson investigator better know what a natural fire is. Because you're never going to convict anyone of setting a fire for insurance money if you don't want to know what a natural fire is. And in studying a natural fire, the arson investigator probably says, wow, I know how damaging a fire can be regardless of who set it. When we look at the history of climate, we see CO2 as a really important control. And we learn the changes in climate in part by seeing what it did to living things, and it was big. And then we go and we look at what we humans are doing, and it's bigger. And so yes, climate has always changed, and that gives us very strong confidence that if humans continue on a path of burning fossil fuels, emitting the CO2, we will cause very large, very long-lasting changes that affect living things in very fundamental ways. And the more you know about the history of climate change, the more impressed you are by what we humans could do to it.
More students. These questions are fantastic. There's one back there.
Right, so more examples of adaptability and resilience in dealing with the coast or with anything else. And I'll be very honest. I'm a geologist who does ice sheets. And so I'm probably not the best person to answer that. And I would bet there are people in this room who can answer better. You start, I believe, so I've talked to some people about this, and one thing you do is you start with getting rid of perverse incentives to do the wrong thing. So you don't want to pay people to go build expensive things in the way. You probably want to look very carefully at getting accurate assessments of what happens if you do it wrong. I've seen a lot of estimates of if we build a wall, it is 100% guaranteed certain to be safe. There's a lot of people in New Orleans that lived behind a wall before Katrina who would doubt that statement. So how often do walls fail? And what's the cost of that? And if you put that in, how much better might it be to start thinking about retreating in an orderly fashion or building things up or looking at phased transitions rather than hardened transitions? And you start thinking about some of these really bright engineers and architects that are around here, your school, and having this sort of, I think this goes on, actually. What's the design competition? What's the next thing? And get the students thinking. Because this is going to take thinking out of the box a little bit. And I know this is happening. And I can't tell you chapter and verse, but I know it's happening. And you start saying, fine, the senior design project is how do we unharden the coast in a way that we get energy out of it, in a way we get protection out of it, in a way we get a buffer out of it that respects nature and respects people.
I'd like to open up the questions to the entire audience now.
Hi, thank you, Professor Alley, for a great talk. So extending your comment before about how fast change is happening in terms of the CO2 temperature rise and the radiative forcing, is there any indication that the ice sheets are responding to the rate of change in addition to the level?
Right.
In terms of dynamics?
So the question whether we're seeing a rate of change as well as the level. So, and I gave a seminar over at the department at MIT yesterday. That's what we're afraid of. So far, the ice sheets sea level is rising just under a foot a century, and that's because we're warming the ocean and it expands, because we're melting mountain glaciers and putting their water in the ocean, and because we're melting ice sheets. And a sort of a third of each. But so far, nothing has run away and gotten crazy. But we can see ways that it might get way worse. And you look at the expectation from the United Nations is that if we don't change our way, we burn like crazy. By late in this century, you get 3 feet. And the uncertainty is 2 to 4, but maybe 15, right? And unfortunately, that particular pattern is one that shows up in a lot of aspects of this discussion. That if we don't change our ways, we burn like crazy, we make it really hot, there is some expected cost. And it may be a little lower cost and a little higher cost or a lot higher cost. Plants. CO2 is plant food. Plants like it. And if you give them more CO2, they grow better. But not a lot, because plants care about so many other things. But if you get it wrong, if it gets too hot, the plant dies. If it gets too cold, the plant dies. If it gets too wet, the plant dies. If it gets too dry, the plant dies. If you don't fertilize it, the plant can die. My dad used to kill my mom's flowers by over-fertilizing them, okay? And if you don't have the pollinators, you don't get the crop. And so you're raising bees. But if you gotta have the pollinators or you don't get the crop, it's equivalent to plant dying. And if you get the invasive smut or the invasive rust or the invasive virus or the invasive whatever, your plant dies. And so you say, fine, we have known about the CO2 making the plants happier for a long time. Maybe it'll do a little better, or maybe it'll a little worse, or maybe it'll kill them. And that distribution of a little better, a little worse, a lot worse keeps showing up in a whole lot of these. Sea level rise can't be a whole lot less, but it can be a whole lot more. And so the sort of, you will hear people say, shouldn't we wait till we're sure? If you look at the true distribution of the uncertainties, the less you trust me, the more you might be worried. And really, it ultimately comes down to something like this, right? I have my cell phone here, right? A little old one, right? You can't make a cell phone with a hammer, but you can break it with a hammer. You can't make the Garden of Eden just by turning up CO2, but maybe you can break something in ways that you don't like.
More questions?
So when you showed that graph of 440,000 years, things came to a peak, came to a peak, came to a peak, and the point was always about the same width until the most recent one, and the point's getting wider and wider. So every year you hear, oh, this was the hottest year. Well, no, wait a minute, now this is the hottest year. Why do you think, I mean, this is a psychology question, I suppose, but why isn't that enough proof for people?
Right, so the 440,000 year thing, why aren't people getting, I don't know, right? So this 440,000 year thing grows into huge, huge things. I have had more, I've on several occasions, I've had chats with senators that they've showed me that and says it's all natural cycles and we don't matter. The truth is, over 1,000 years, the changes from that are so slow that they really don't matter. That one is, if you stretch that out to year, they really don't matter much. And so the change in the next 1,000 years from changes of features of the Earth's orbit is really small. The change from us burning fossil fuels is really big. And the CO2 will make it warmer. And we understand this. And so I, as you said, it may be a psychology experiment. And I'm not sure I could answer it. You might be able to answer it better than I can.
I'm an architect, I can't.
She's an architect, but you're one of the important people who can help solve some of these issues. So you're an important person. Thank you. Okay.
Question here.
Can you say a little more about what causes CO2 during the glacial cycles? What changes in the circulation of the atmosphere of the ocean that causes CO2?
So why did CO2 change during the glacial cycles? And there isn't a glib answer. There's probably about 5 or 6 pieces of it. But I'll do one of them that I think is important here. And so let's go back a minute. Did it ever bother you that the ocean is blue and not green? This is a fascinating question. You know, the ocean is blue and it's not green. But there's lots of sun, and there's lots of CO2, and there's lots of water, so you can grow plants out the wazoo. But it's all, and you know, there's some mixing and some other things in there, but a lot of the problem is that there isn't enough fertilizer. And the moment you put a little bit of fertilizer in the ocean, a plant uses it and grows, and then the plant gets eaten by an animal, and then the animal poops or dies, and then it sinks. And in doing that, the fertilizer gets taken into the deep ocean, and so does a lot of CO2, because the plant is just CO2 and water turned into plant. And every wave mixes bubbles and sprays with the atmosphere, so the plants are essentially growing in the air, even if they're in the ocean. So there's this steady flux of CO2 into the deep ocean, along with this little bit of fertilizer, and then more plant doesn't grow for a while. And now the question is, how fast does it come back up? Right? There's these huge ecosystems down there that are waiting for manna from heaven, you know, poop particles, right? And then occasionally a whale falls, right? It's a bizarre ecosystem, right? Because there's all these little worms and things living on the seafloor, and then boom, a whale falls. And then they have these flowerings of amazing stuff, these zombie worms that burrow into the bones, and we probably caused all kinds of extinctions on the seafloor that we never knew about by killing whales, so that whales didn't fall for a while. But what happens then is all this stuff falls down there, and it burns the organic matter and releases the CO2 into the deep ocean. And then the question is, how long does it take that CO2 to come up? And in the Ice Age, you get more sea ice and you shift the winds, and it seems to have made it harder for that CO2 to come back up. So it stayed in the deep ocean rather than mixing back to the surface. So as you took CO2 out of the air and ran it down into the deep ocean, it had troubles coming back, and so there was a little less in the air and a little more in the deep ocean because of moving the winds and moving the sea ice in ways that made it harder for it to get back to the surface.
I have been favoring this side of the audience lately. I want to go there.
Since you mentioned fertilizer, I remember reading a paper back in college many years ago about something called Iron X, where they fertilized the algae down in the Antarctic. The argument of the people that wrote it was that if you did it on a large scale, it would actually pull a substantial amount of CO2 out of the air. Is that, I never heard about it afterwards. Is there a reason?
Right. So this is a great. So if you didn't hear, one of the ideas of why the CO2 was drawn down, the Ice Age has more dust, and that's fertilizer. So you make more plants that can sink, and so that pulls the CO2 down a little bit. And in particular, it was iron, because mostly the ocean is limited by phosphorus or nitrogen. Nitrate fixed, but there's a few cases that it might be iron or maybe something else, zinc or something. And so the idea was you fertilize and then that grows more plants and then they get eaten by animals and they get pooped and that sinks and then that lowers CO2. And so then the idea was maybe we could do this. And so there was this famous quote about give me a tanker full of iron and I'll start an ice age. You probably can draw down a little CO2 this way. You can't do a lot. First of all, if you draw down too much, you get all this sinking stuff down there, and then you start making it anoxic because there's lots of decaying stuff, and then you start kicking out nitrous oxide, which is worse than the CO2. And so you can't do a whole lot. You probably could. If we wanted to tweak a little bit, it probably would be doable. Tweaking a lot, probably not. So, you know, in a world where if the world said, we will stop at 1.5 degrees C warming and we will not let it go past for anything under the sun and we will use every tool available to us, maybe we'd look at that. In a world where we said, we want to make sure the tropics are still habitable, it's a little term and next to big ones.
So we have just a few more minutes. There was one question there, but I'll take one here first.
Do we assume that we've already reached, so to speak, phase one of damage irrecoverable? And what even in the next 10 years, if humanity changed the direction of the amount of CO2 emitted, there is still problems that could multiply or increase. I assume in your discussion that's already implied and implicit.
Right, so the question, if you did not hear, have we all sort of committed to damage? We've committed to some damage already. It is fairly clear that the costs of global warming go up faster than the temperature. So the first degree of warming was pretty cheap. It's almost free. Because, you know, we've always lived in a variable world and, you know, so, you're used to adapting and going with the flow, and so you bend a little bit. But we've had the first degree of warming. And the second degree of warming, the crop that you're used to growing here is now going to have trouble, and maybe you're going to have to grow a different crop. But there's somebody in a warmer place that you can borrow from, you can learn from. It'll cost you something to do that, but you'll figure it out. But then the third degree of warming, there are people in the world that can't go borrow a crop from a hotter place because there isn't one. And then the fourth degree of warming, you start getting places where you can't work outside and maybe you can't live outside because it's too hot. And so you sort of think of each degree as costing more than the previous one. And what that does, it changes the look a little bit, which is instead of saying we're doomed, you say whenever we get started, we just avoided the worst. because the worst is whatever is about to come, and it will get bad if we go too far. But right now, we still are well away from the really costly things, and we can still take measured changes. I believe it is still safe to say that when the economists look at it and say, what do we do to balance the needs of the present against the needs of the future, that they say, don't panic, just get started.
The insurance industry is already acting that, even though they're businesses, they are already charging based on global change and flooding.
So the comment being that the insurance agencies are, the reinsurance industry in particular already gets it, yes.
There was one question from this side of the room. Does this person still have, no more? We have 2 minutes for a question, so right here.
Hi, can you share two questions? Can you share with us briefly what your daughter's doing on Everest?
Oh.
And second, you said that in your lifetime you've gone from a great amount of ignorance to a great amount of knowledge. So in the rest of your lifetime, what is the one or two things that you'd really like to see us learn and know about?
Right, so the one daughter is teaching middle school science, the other one is a grad student studying Antarctic ice shelves, actually. And she's also, at the moment, teaching hammered dulcimer. She's they just finished her year as the U.S. national hammered dulcimer champion. And the elder daughter is a pretty good fiddler. So I'm the only black sheep in the family who has no musical talent, so my wife does. So the other one was what would I like to see us learn? Boy, I love climate science. I love ice science. I desperately hope that there are students here who come join us or come work with Carrie and with you. That I hope we see people who are at the aquarium and working on this. But I also really hope that some of them are architects and that some of them are material scientists. And some of them are taking what we know about the physical world and using it to help people. The bigger picture of this. I have a public talk that I do in other venues where I walk through the history of energy crises. When the European settlers arrived on Cape Cod, it was goodly wooded to the shore. In the late 1600s, the town of Eastham outlawed your own ability to cut your own tree on your own land because deforestation had become so extreme that the government got in your face. And Cape Cod was deforested from the late 1600s until into the 1900s. Cindy's father grew up on a treeless cape and watched the trees grow back as his kids grew up. And the people burned what drifted across from Maine. And when Thoreau walked the Cape, he said what they call woods are either waist high or you can see the horizon through them. And at another point he said the only trees in the entire town are a line of Lombardy poplars around the town square and they're all dead. And we are the first generation in history that can look at ourselves and look at our students and say they can build a sustainable energy system. And there's a lot of paths to how they can get there. But they do not have to burn something faster than nature makes it, run out and hit a crisis. They actually know how to do it. And they are the first generation in the entire history of humanity that knows how to power the future. And that's wonderful. And I would love to see how we can make that work.
I'm sorry the time is up. I'd like to thank the aquarium for helping to make this possible. I'd like to thank you all for coming, and we all